Welcome back. In this video, we will be discussing the bond angles mentioned in the previous 12 videos. As you can see, for a linear structure, the bond angle is always 120 degrees. And for a trigonal planar structure with equal bonding domains, the bond angle is 120 degrees. Moving on to having the presence of a lone pair, we can see that it pushes the two bonding domains closer together to give an angle of less than 120 degrees. Here we move on to the tetrahedral structure, and we know that the angles are exactly 109.5 degrees. Some would ask, what is the effect of the double bond on the bonding angles? The double bond has a very small effect on bond angles compared to the effect of a lone pair, so we don't usually include the effect of the double bond. However, a double bond does have an influence on polarity, but in an ion such as this, there is constant resonance, so we can conclude that this ion is nonpolar. Here, again, the presence of a lone pair will push these angles to being less than 109.5 degrees. Likewise, in this structure, the angle will again be less than 109.5 degrees. For the trigonal bipyramidal structure, we know that we have an equatorial region and an axial region. Between the equatorial domain and the axial domain, there is an angle of exactly 90 degrees. Whereas with the equatorial domain, between each domain there is a bond angle of 120 degrees. What happens when we introduce a lone pair? As we know, we spin the molecule and we can see that the lone pair is placed equatorially. What is the effect of the lone pair on the angles? We will see a slight deflection of the bonding domains on the axial position and a closing of the bonding angles in the equatorial position. So you need to communicate both of those in your diagram. Here we can see our angle is going to be less than 120 degrees, and the angle between the axial and the equatorial will also be less than 90 degrees. In some textbooks we see that they write the angle here as greater than 180 degrees. Please see The Central Science by Brown, LeMay and Burston for further information on page 355 and with the following structure 356. Now we're going to move on to our T-shaped geometry. Again, we have angles of less than 90 degrees. For the octahedral geometry, we know that all bond angles are 90 degrees. There is no preference given to either an axial or an equatorial position. With the following structure built here, we can see our two bonds coming towards us, our two bonding domains going towards us, one bonding domain flat, and a lone pair at the bottom of the structure. As we said, no preference because all the angles are 90, so we put the lone pair at the bottom. The next lone pair will be located as far apart as possible. It will be put on the top. But back to the bonding angles, what is the effect of this lone pair? If we move the molecule, have a look, it's pushing those bonding domains away from it. How do we communicate that in the diagram? The bonding domains which make up the square planar base still remain 90 degrees. However, the bond angles between the top of the molecule or the peak of our square pyramidal and this square base is now less than 90 degrees. In the final structure, the effect of the lone pairs cancel out and we get left with exact angles of 90 degrees.